So, welcome back again. In this class, we are going to discuss one of the basic problems of physics, that is simple harmonic oscillator problem, generation of phase space plot using Euler method. Euler method is used for solving differential equation, and we are going to solve the problems of harmonic oscillator, which is actually a second order differential equation, and we are solving this second order differential equation using one of the numerical method, which is known as the Euler method, and we are trying to generate the phase space plot of harmonic oscillator. And you have studied what is phase space plot in your classical mechanics paper, and everywhere you are studying it, a phase space plot. So you are going to simulate the harmonic oscillator problem using the Euler method. Basically, the equation for a simple harmonic oscillator is of the form F is equal to, you know well, F is equal to what? F is equal to minus K X, right? And F is what? M into A. M into A is equal to M. I'll have to put it small. M into A is equal to minus K into X. And here we can see the acceleration is proportional to displacement. And from this I can write what? K by M is constant and omega square. Omega square is what? Omega square. Here I'm having omega square. Omega square. Okay. So omega square is equal to K by M, and from this I'll get the equation what? Acceleration is equal to minus omega square x. Okay, this is the equation for acceleration, and from that I can get acceleration is what? Acceleration is what? Acceleration is basically dv by dt. dv by dt, right? dv by dt, or I can write it as delta v is equal to a delta t, and similarly delta x is equal to v delta t in a similar manner. And this is what is happening in Euler method. And from this equation I'll get the new velocity vi is what? Actually the old velocity plus a delta t, and this is actually the Euler method. Euler method for solving differential equation. Euler method, it is not so accurate method, but it is one of the simplest method as far as the solution of differential equation is considered. Euler method. Okay, so what happens? You will get to expression for new velocity and expression for new position in terms of old position. So we can draw the x versus time graph, you can draw the v versus time graph, and we can also draw the x versus v graph, and this x versus v graph is known as the phase curve. And you have studied in your mathematical physics paper and classical mechanics paper the phase space diagram of harmonic oscillator. You just try to recall it, what is the space diagram of different linear and non-linear systems. Okay, so we'll move on to the program. That is, before going to the program, we'll discuss what is the algorithm. So, in the beginning, as usual, you'll have to start with one start. Then we'll take the number of steps required for the iteration, and let us assume to be n is equal to 50. Okay, so what all things are needed? X is needed, T is needed, V is needed. I can initialize a list or array. Okay, so here what I'm doing is initializing array as X, T, V and A with all elements as 0. Okay, we can initialize a list or array, and we get we will give initial values for position, velocity and omega square. Initial position is given as 0, initial velocity is given as 2, and omega is given as 1, and dt, which is the time step. We know omega is equal to what? And we know what is omega. Omega is equal to 2 pi nu, and nu is what? frequency. Frequency is the reciprocal of time period. And if there are n small intervals of time, I can write total time period is equal to n into dt. So I have the expression for my frequency nu is equal to 1 by n into dt, and substituting this new value in this equation for angular frequency omega, I'll get the expression for small increment of time delta t is equal to 2 pi by n into omega. 2 pi by n into omega. The same thing is given here, dt is equal to 2 pi by n into omega. Here it is given as 2.1, or you can give it as 2.0, 2.2, etc. Okay. So what is next is acceleration. Acceleration is equal to minus omega square x, and it is given here the initial value of x into omega square, and what is given here, omega is given as 1. Okay, and for I is equal to 1 to do 1 to n do. This loop works for how many times? N times, depending upon the value of n I have given here, and it is 50. So the loop works normally up to 50 times. And you write the expression for acceleration. New value of acceleration is what? Old value of position into omega square, and new value of velocity is old value of velocity plus acceleration into time increment. And similarly, new value of position and new value of time is also shown. Okay, next what you have to do, you can plot x versus v graph, which is the phase space plot, then x versus t, x v versus t, velocity time graph, position time graph, etc. And what is this one? This is not necessary. 13, 14, and here it is 15, 15. Stop. Right. And moving to program, if we are using the command from pylab import star, means all the functions defined in the pylab module can be used by us. And here I have given as for a number of iterations in the loop is n is equal to 50, and have initialized an array, that is array for position, time, velocity and acceleration to be zeros, and with n number of data points, and the data type of this data points is initialized to be float. And we have initialized x0 0 initial velocity 2 and initial omega value to be 1. And similarly we have given the same expression for dt and acceleration, and it is the same repetition of the algorithm what we have written for I in range 1 to n. We write all this all those we'll write all those codings that is required to be in the loop. Then we'll come out of the loop when once the I value reaches 50 or I value reaches 49. Range starts from 1 to 49, and what happens is that we'll get 49 values for acceleration, velocity, displacement and time. Now we'll draw a first graph, that is figure 1 I have given. It is a harmonic oscillator phase space plot, and it is a plot between position and velocity. Grid true means you will get horizontal and vertical lines as in the form of as it is there in graph paper, and we'll give plot xv. And the next figure is figure 2, and in that figure 2 I have included subplots. Two more plots are there, that is 1 2 1, that is 1 row 2 column, and in that first one, and it is the position time graph, and the second subplot is velocity time graph, which is you can just give it as figure 1 2 3, or you can draw it, as you wish. Okay, you try to develop your own coding for this program and all. It is very simple program, and you can manipulate it using different functions of plotting and all. Try to explore more. Okay. And what is the phase space of an harmonic oscillator? And what you got is a circle, and circle was the phase space of an harmonic oscillator. And it is the position type graph. And what is velocity? Derivative of position. If position is a sine curve starting from 0, you got the same sine curve with 90-degree phase shift. That is what? Derivative means you'll get cos, right? That is only the difference. If it is sine curve here, it becomes a cos curve for the velocity time graph. And you'll just know the beauty of the physics through this all plottings and all. Things become more clear to you. The sine curve, position, velocity, derivative of position, sine becomes cos with a phase shift of 90 degree. Okay, interesting. So, two portions are to be covered in harmonic oscillator. The first one discussed was the ideal case. Actually, in the realistic problems, all sorts of harmonic oscillator motion analogies that is happening on the earth is what? It is never ideal. A lot of damping forces, which what happens, which prevents the motion and which damps the motion and which makes the harmonic oscillator come to rest will be there. And here also we'll discuss the damped harmonic oscillator method also. And in this case, what have we used? We have used Euler method for solving the differential equation, and here we have just slightly changed the algorithm. It is called Feynman-Newton method. Euler method I have told you earlier, and I will discuss in the accuracy consideration also. Euler method is having a lot of disadvantages or lot of discrepancies. To avoid that, we use the Feynman-Newton method. Okay, so in this we consider the case of a damped harmonic oscillator. So what happens here is that damping force is what? It is a dissipative force. So dissipative forces are velocity dependent forces. And here my damping force is expressed as F damped is equal to minus C into V, where C is the damping coefficient and V is the velocity of the oscillating mass. And what happens? The force acting on a damped harmonic oscillator becomes F is equal to minus Kx minus Cv. X as a function of time and V velocity also as a function of time. And how can I write this? How can I write this? In a usual form, force by mass is equal to dv by dt, which is acceleration, and acceleration is dv by dt, and velocity is dx by dt, and this is how you solve it using Euler method, and this is the Euler method forms, writing the acceleration and velocity in terms of its derivatives. Okay, so a better way, we are trying for a better way which gives a better results than avoiding the errors, and this is the Feynman-Newton method. And here what happens, it is actually also known as a half interval method. And if we are having a function f of t such that the derivative of function is represented as q of t, and it is obtained by using the value of function, and the value of the function at a time interval delta t is obtained. That is, the value of function is obtained by using a value of function q of t halfway between t and t plus delta t. That is, f of t plus delta t is equal to f of t plus delta t into q of t plus delta t by 2. It is also known as half interval method. Just including a simple line of coding in your basic problem changes it into a Feynman-Newton method. Okay. So damped harmonic oscillator, Feynman-Newton method, and we have dx by dt is equal to v, and dv by dt is what? Minus omega square x into bv. And here b is the damping constant. I can use b or I can use v or anything. I'll write it as c. Okay. And here also I'll write it as c. That's all. C is my damping coefficient. So you can try writing an algorithm for this. Same repetition of the program itself is the algorithm. And from PyLab import star, I have given the initial values for position, velocity, omega, and I have given the damping constant to be 0.05, and initial time is given, initial step size is given, step size h is equal to 0.01. And in the first case, what we have done was with arrays, and here I have used list x dat, v dat, and time as the three lists, and here it is for storing position data store here. Okay, that's all. Store here. You can give all any type of expression, any types of comments by putting hash. It won't be read by the interpreter. Any types of comment can be made by putting a simple hash and writing your comments after that. Okay. Now it is the Feynman-Newton algorithm step. Feynman-Newton Newton method. This is the step that makes it a Feynman Newton method. New velocity is what? Old velocity plus h into minus omega square x minus b v0 minus b, it's minus c v0 by 2. And now what happens while t less than, I have given a time t less than or equal to 250. You can vary this time. X is what? X is equal to x plus h into v0. Similarly, velocity is what? Velocity plus h into minus omega square x minus, uh, instead of bl, right, c v0. That's all. You'll get a series of values for position, velocity, and time t is equal to t plus h, and you'll get uh, figure 1 as usual, damped harmonic oscillator, that is position versus time graph. Second one is figure 2, velocity term time graph, and the third figure is what? Damped harmonic oscillator. It is what? The phase space plot, right? Harmonic oscillator, and I'll have to write the phase space plot. Okay. Okay, you can just go through your previous year's notebook. You can see the phase space plot of a damped harmonic oscillator we have discussed. It is the plot between position and velocity. And you can see the output windows. It is what? It is the position versus time graph. And just it will be, the first one will be sine curve, means this one will be a cos curve, and it is damping in the sense that velocity comes to 0 after 250 iterations, and the circle or the ellipse that you have obtained in the previous case has turned into a spiral. In the case of a damped harmonic oscillator, that is phase space plot, has turned into a spiral. Okay, you just go through the thing. You'll have to keep in mind that wherever you write big program, you have to write the algorithm for also. In some cases, I've left the algorithm for you to write. Okay, I've given the algorithm for most of the programs, and hope if you're going through this algorithms, the steps or methodology is clear for you. It is just simply the repetition of the program. So try writing the algorithm for Feynman-Newton method also. Okay, by going through the algorithm written for the harmonic oscillator problem. So you just go through it. If you are having doubts, you just try coding in Google Colab. Okay, try coding in Google Colab and send me the for topic of your like plot you have obtained. Okay, thank you. So see you in the next class.